All right, so let's get started. So my name is Eric Broomer. I'm a developer. I work on the C++ compiler optimizer, so doing code generation and optimization. And this talk is, native code performance. There's a lot of stuff that's been going on in the conference so far that's sort of web-focused, service-focused. But this is going to be a pretty deep talk about how memory affects native code performance. So first, the question for you guys. C developers, native code developers, let's see the hands. All right, a lot of people. That's awesome. Another show of hands. Who cares about performance? Good. So, all right, I want to start off the presentation with a question. So, who believes that less instructions yields faster code? So, we're talking the number of floating point operations per second, per frame, per iteration, per whatever. Show of hands, who says less instructions yields faster code? All right, we got a few hands. And, to some extent, that is true. But, a real quick example, I got some code on the left over there, and I got some code that does exactly the same thing on the right. The code has 3 times more instructions. The code consumes 30% more memory, yet it goes 5 times faster. We'll get into what that code actually does later. So look, less instructions is not the only prescription for performance out there. I really want to talk about memory. Memory really does matter when it comes to performance. Things like the working set, how much data memory your program actually uses, how you handle caching, and then spatial and temporal locality of accesses. And memory is absolutely critical to performance for modern code running on modern processors, especially high-performance code. And sometimes it's critical to performance in non-obvious ways. Now, when I think about memory when I'm writing a C or C++ program, right, this is mostly what I think of. I think of how do I allocate my memory? Is it on the stack? Do I use malloc or calloc or new, or you're using C++, you're hopefully using make shared, stuff like that. But there's a lot more to it, especially when it comes to performance. So really the goal of this talk is a real deep dive, lots of code that's going to be shown, into how the performance of native code is really affected by memory. Memory, the elephant in the CPU. So this is a pretty big agenda, but basically I want to give a brief overview of caches and then just go through a whole bunch of examples just to show things of how memory really affects performance. We're going to go over things like access patterns, parallelization, vectorization, code alignment, and then a few interesting edge cases. So let's get to it. So this is a single core from the Intel Sandy Bridge chip. Sandy Bridge offers 6 pipelines per core. What that means is at peak performance, it can execute 6 instructions on every single cycle. More importantly for this talk, each Sandy Bridge core has 64 kilobytes of L1 cache that's split half between data and half between instructions, and a 256 kilobyte L2 cache. But it's sort of, it's only part of the picture when it comes to the Sandy Bridge stuff. They're really 4-core processors. So on a given die, you've got 4 cores. Each core has 6 instruction pipelines, so each core can execute 6 instructions per cycle. Each core has 64 kilobytes of L1 cache and 256 kilobytes of L2 cache. And then there's a shared L3 cache. And on the desktop version of the chips, you've got around 8 megs of L3 cache. And on the server, the Xeon chips, you can get up to 20 megabytes of L3 cache. Now, something really important that you can get from this diagram is around, somewhere between a quarter and a third of the chip is just cache, right? And if you're looking at a specific core, it's around half. Half of the actual area spent on the die is just spent in cache. Cache is extraordinarily important. Memory is extraordinarily important. This is a different view of that same chart. It's more of a functional diagram. So I've got I've rotated it, I guess. I've got the execution pipelines, the 4 cores on the far left. Each core has its own L1 cache, its own L2 cache. There's a shared L3 cache, and then main memory. Yeah, it's not the prettiest of charts. I apologize. I'm not great when it comes to that. I'm also not very funny, so keep that in mind. So let's look at instruction or memory latency, so how long it takes to access each bit of cache. So let's say we're at that second pipeline and we issue a load instruction. We want to load 4 bytes from the L1 cache. That takes it takes 4 cycles to do that. And in 4 cycles, you can take two 32-bit numbers, multiply them, and produce a result that's consumable by another instruction, just to give you a sense of how long it takes to get to the L1 cache. Anyone hazard a guess of how long it takes to get data from the L2 cache? Just 4 bytes. How many multiplies can we do? We can actually do a lot of multiplies. It's 12 cycles to access data in the L2 cache. It's around the same amount of time that you can take a 32-bit number, take its square root on the chip, produce its result, and be consumable by the next instruction. It's kind of interesting that you can do a square root in the same amount of time it takes to get data from the L2 cache. And the important thing is once you've accessed something from the L2 cache, that data and the data near it on the same cache line are populated into the L1 cache. So the next time you access that data or somewhere near it, you don't have to pay the penalty of going to the L2 cache. You can just stick with the L1 cache. And that's why caches give the benefit that they do. Similarly, to access data in the L3 cache, it takes around 2 32-bit square root operations. And then we've got accessing, you access your stuff in the L3 cache and it populates the other caches so you don't have to go to the L3 cache for your next piece of data. If you're accessing 4 bytes from memory, right, just 4 bytes, you have to access memory for it. Processor does whatever it would do if the processor just took a coffee break. And it can sometimes get a little bit worse than just the coffee break, right? There's different levels of performance hell when it comes to accessing memory. If you're lucky, the data is in the memory that's attached to your processor die. In modern processors and non-uniform memory architectures, you can have different banks of memory physically located on different parts of the chip. So maybe your data is not on your memory, but it's on another processor's memory. And that's going to take even longer to get the data. Worst case is you have to go to disk. And that's, accessing from memory is a coffee break. Going to disk is, I don't know, like a sabbatical, I guess, a year-long sabbatical. So look, from that last chart, it makes a lot of sense. You want to keep your data as close to the execution units as possible. Hopefully you guys know this already. I mean, that's sort of, that's the stuff that they show. I think they even talk about this stuff in high school now. That wasn't a joke. So let's get started with an example. The first one I want to talk about is matrix multiply. This is the simple code to take a matrix A, just a 2-dimensional array, A, multiply it by the matrix B, and put the result in matrix C. This code sucks. This code's really, really, really bad. And it's hard to figure out why just at a glance. But if we look really carefully at that access of B sub K sub J, that particular access has really, really poor spatial locality in the cache. What that really means, the way to think about this is if you look at how B is organized in memory, it's just a big stream of bytes, even though it's a 2-dimensional array. And it's organized with the first row of bytes, followed by the next matrix row of bytes, and so on. So if we took, say, J equals 5, and we're accessing elements on each iteration of the K loop, we're accessing B sub 0 sub 5, and then B sub 1 sub 5, and so on. And the problem happens if your matrices are huge. So if you're talking about like a 10,000 by 10,000 matrix or bigger, a million by a million matrix, those accesses are really, really far apart, and you're accessing them from the innermost loop. That's what I mean by poor spatial locality. You've got an innermost loop accessing data that could be miles away from the previous access, and that's going to yield a lot of coffee breaks, as it were. So this code is awesome. I haven't changed anything about the innermost loop body. It's still C sub I sub j plus equals blah, blah, blah. The only thing I changed here is I've swapped the K loop and the J loop. That's the only thing that I did. I haven't changed any data structures. I haven't changed any of the code in the innermost loop. It's just swapping those two loops right there. And now if you look at accesses in the innermost loop with respect to that B sub K sub J, we're now accessing B sub 0 sub, say, J equals 5, and then B sub 0 sub 6, and 0 sub 7, B sub 0 sub 8. And the deal is, the first one might miss in, say, the L2 cache or the L3 cache. But because you're accessing data that's immediately after the one you just accessed, these are going to hit in the L1 cache, almost certainly. So this is going to give a performance improvement. For a 10,000 by 10,000 matrix, anyone hazard a guess at what the performance improvement actually is? If you've seen this before, it doesn't count. It's not fair. Is it a 10% improvement? Is it a 20% improvement? Man said the magic number. It is 10 times. In fact, it can be more than that. On a really, really powerful processor with a great memory system, the benefit here is around 10x. If you've got a really crappy processor with a crappy memory system, I've seen that number go up to 18x. And the deal is, right, we haven't changed any of our data. We haven't changed really not much of the code. All we've done is we've swapped the two inner loops, just entirely focusing on one single memory access. And it just means we're changing the order in which we're accessing memory, and that's going to give a huge, huge speed up. So, the same performance statement as before. You want to keep your data close to the execution units as possible, but you also got to watch your access patterns. How you guys doing? Is that okay? Oh, we got a question.
Just real quick, how come the compiler doesn't fix that?
Good question. So the question was, why doesn't the compiler just fix that? It will. So with the Visual Studio Preview that we, I think was sent out with this, we don't do the optimization of loop permutation or loop interchange where we do that, but we are working on it. We're going to do our best to make sure it shows up in RTM. And that's right, using full data dependence analysis to make sure that whatever code you have is going to access the caches in the best way possible. One more question. How far away do two things have to be before it's a cache miss? That really depends on what you're doing. We'll get to an example in the vector code section where we're accessing 32 bytes of data at a time. So, two accesses worth, you're going to have another cache miss. If your data is completely contiguous, that's sort of the best that you can do.
So how long are the cache rows typically?
Cache lines in the L1 and L2 cache are generally 64 bytes on modern processors, which actually seems pretty small, but chips are pretty smart nowadays. As long as you keep your data fairly contiguous and access it fairly regularly, as regular as you can, that's going to give you basically the best performance. And that's not fair. You asked me a question that I'm only going to get to at the end of the talk. All right, let's move on to some multi-core effects. So here I've got a function that just takes 3 array parameters. They're float stars. I apologize. You can do vector float or any of that. I'm mostly a C programmer. And we're just taking a sub I equals b sub I plus c sub I, and the bounds of the loop are huge. We're going from 0 to 4 million. And I have access to a pretty powerful machine. It's got 40 cores on it, and I want to parallelize this particular for loop as best I can on that 40-core machine. So, I tried it, parallelizing using 5 cores. Oh, sorry, what I mean by parallelizing here. So let's say I wanted to parallelize across 4 cores. I'm going to take the loop iteration space, cut it into 4 equal chunks, and then ship off each chunk to a different processor. So if it's going from 0 to 4 million, if I wanted to parallelize to 4 cores, the first million iterations go to 1 core, then the second million iterations go to the second core, and so on, and then all the cores can execute in parallel. That's what I mean by parallelize in this case. So if I took this loop body and parallelized it across 5 cores, I only get a 1.6x speed up. And that's okay. I parallelized it to 10 cores, and I only got a 2.4x speed up. And that sucks. So, I got to ask the question, why does that suck so much? That's not a very fair question to ask. So instead, I want to ask the question, how much time is actually spent loading memory? Keep in mind, this is a memory talk. So someone, how much time in this particular, the context of this loop body, how much time is spent loading data from B sub I and C sub I compared to adding them together, compared to doing the I++ and comparing I is less than 4 million? Anyone hazard a guess? 99%. Okay, good. Yes, all of the time in this loop body is spent loading from memory. The time doing the add and the comparison, they basically comprise 0%, 1%, 2%, whatever. It doesn't really matter. It's all spent in memory. And that's the place to focus on when we're doing parallelization of code. So this is an architecture or just a functional diagram of what that 40-core machine that I have access to looks like. Huge amount of memory, just 32 gigs, I think maybe even 64 gigs of memory on this guy. And then there are 4 dies on the motherboard. Each die has 10 cores on it. Each core has a 64 kilobyte L1 cache, 256 kilobyte L2 cache, and a 30 megabyte L3 cache. 30 megabytes, it's huge. There's so much cache available on this machine. It's insanely powerful. But what really matters is what my data is. So I'm accessing 3 arrays their float, so that each element of the array is 4 bytes, and I'm accessing 4 million. You do the math, it ends up actually being 48 megabytes of memory. So I'm accessing 48 megabytes of memory. I want to parallelize that across multiple cores. So if I'm only using 5 cores, I'm really only have access to 30 megs of L3 cache. That's just not enough, right? It's not 48 does not fit into 30. Just not enough memory. If I parallelize to 10 cores, again, it's still not enough. There's just not enough cache available to it. That's why the speed up sucks. However, when you switch to 20 cores, we now have access to 2 L3 caches. Overall amount of memory available on the chips is going to be 60 megabytes, and 48 megabytes, last time I checked, is less than 60. And that's what we get from it. So when you parallelize on this machine on 20 cores, you get an 18x speed up. Now, to be honest, my columns here are a little misleading. The number of cores, the thing that's on the far left, just really doesn't matter. Right? The only thing that matters is the amount of cache that's available for your program. Right? The second column is the thing that's actually driving the speed up. The number of cores is not. I think that's pretty interesting.
So when you run on 10 cores, why does it only put them on one chip? Why does it split them up between multiple chips?
So the question is why, this is a very good question. So if you're parallelizing across the 10 cores, why are all the 10 cores going to be on one chip? Why don't you spread out 5 on one chip, 5 on another? That would make a lot of sense. Parallelization techniques are extraordinarily hard. For the most part, you really do want to keep as much of your program in the same physical location as possible. I'm pretty sure that's sort of the most common way of doing it. So I mean, even like the Microsoft, the Parallel Patterns Library or Concert, or I forget what the concurrency runtime. That stuff, they try as best as possible to keep tasks that work on similar data on the same node. And that, for the most part, that actually is a good thing, especially in terms of sharing. So if you've got multiple cores that need to share data amongst one another. So let's say you've got something in your loop body where you've got data being written from one iteration and read from another iteration, and that data needs to cross from one core to another. That memory, that dependence really happens in memory, or really happens on the caches, and you do want to keep that as close to the chips as possible. So for the most part, so this is a really long-winded answer to your question. I'm a long-winded kind of guy. That's sort of what's really going on. But still, it doesn't really matter, right? The only thing that matters is you need to have the cache to hit the data set that you're looking for, to hit the working set that you're working for. So the same performance statement before, keep your data close and watch your access patterns, especially when multi-threading I/O-bound code. And we'll talk more about this in a little bit, but a lot of high-performance code these days is totally I/O-bound. What I mean by I/O-bound is really memory-bound. I'm a compiler guy. I think about things in terms of the processor. So either it's CPU-bound code or it's not. So I call it I/O-bound code, even though it's really just accessing stuff from memory. You guys okay? Making sense so far? Nothing too crazy. So let's move on to a cool example. Hopefully you've seen this program before. I think they demoed it at the last Build Talk. It's a demo that we've been showing for some time. It's really just I'm not a fan of this mouse, I'm sorry. Just click. There we go. It's a pretty basic physics demo. So we've got 4,000 particles. And we're computing the gravitational force of every particle on every other particle and using that force information to move the particles. Rinse and repeat as fast as you can. And the metric that we use for that is the frames per second. So, FPS is reported in the application. So, the higher frames per second, the better performance you're going to get on this. There we go. So this is Newton's gravitational formula in vector form. I don't really want to get into it. I apologize if this brings back terrible memories of high school for you guys. I really liked high school physics, but this is a slight simplification of the above. What I really want to get at, of course, is memory. That's the whole point of this talk. So what's really important is the data structure of these particles. So what we've got is each particle has position, velocity, and acceleration. And each of those is a vector, has an XYZ component. And then we've just got an array of these particles. In this case, we've got 4,096. The way the particle structure is laid out in memory is just, again, a flat stream of bytes. And because of the way we've used an array of structs, we've got the position right next to the velocity, right next to the acceleration. It's the x, y, and z components, and so on and so forth. And that's our data structure that we've got, and that's what it looks like in memory. So onto some code. The overall structure of this is a doubly nested for loop. So there's for I equals 0, I is less than the number of bodies, 4096. Then there's innermost is the j loop, j equals 0, j is less than 4096. And all we're doing is we're taking the ith particle, computing the net gravitational force of all of the other particles, all jth particles, and then we're going to use that information to move the ith particle. This is pretty straightforward. What I'm interested in is the body of the innermost loop, and that's what I'm going to show right here. So we need to compute the vector distance between the first particle and the second particle, so the ith particle and the jth particle, and that's what goes in this R thing. And then we compute, the gravitational parameters. It's the square root of the sum of the sum of the x, y, and z components squared, that kind of stuff. And then we have this computed net acceleration vector that gets incremented with each for every j particle. Right, enough of the physics stuff. Let's just talk about this as if it were C code or C++ code. So in this innermost loop body, we've got 3 loads. Right, we're loading particles sub j dot position x, position y, position z. We are loading the ith particle as well. But for the most part, any compiler worth its salt is going to take those and hoist it outside of the J loop. Right? Those loads aren't going to change. There's no point in actually loading from the caches every single time. So those don't really count. Those are going to get hoisted outside the J loop. The data is going to get stored in a register, and the register is going to be used. So yeah, not to worry about that. We've got 8 additions and subtractions. We've got 9 multiplies. We've got a call to square root, and we have a divide instruction that's in this loop. So those are all the operations that it takes to compute, that formula on the left, at the top left of the screen. So here's some performance numbers. On the left side, I put the scalar info sort of just to have as a baseline. So there's 4,096 iterations of the innermost loop, and we get around 8 frames per second. That's just a good baseline. Visual C++, we have automatic vectorization that targets 128-bit code. So what's really happening here is we're executing 4 iterations of the J loop in parallel on a single core by taking advantage of the SSE2 instruction set. And we get, you can see the number of loop iterations goes from 4096 to 1024. It's just divided by 4 because we can do 4 iterations at a time. And the number, the frames per second, it goes up, which is good. It's around 2.3, 2.2x. X higher. But the processor that I was running this particular benchmark on also supports the AVX instruction set, which is 256 bits. And I compiled the code targeting 256 bits where we do 8 iterations of the loop at a time. And the frame rate, it does go up, which is nice, but it doesn't go up very much. We're executing 1/2 of the number of iterations as we did in the 128-bit case. What the hell's going on right here? This sucks. So question for you guys. Let's look at that innermost loop again. What's hot? Right, we've got 3 loads. We've got that hoisted stuff, and that doesn't count. We've got a square root, a divide, 9 multiplies, and a bunch of additions and subtractions. Anyone wager a guess at what the processor is actually doing? It's accessing memory. Yes, of course. That should be clear by now. The answer to most of my questions is going to be memory. Yeah, from the processor's point of view, it's spending more than half of the time not just accessing memory, but handling these 3 loads. So it doesn't really matter. You could add another dozen multiplies to this, and it's not going to change the frame rate at all. You add more divisions, more square roots, it's not going to touch the frame rate. Really, most of the time that's happening here is spent handling a load of particles sub j dot position x, position y, position z. And I want to dive pretty deep into showing why that's the case. So keep in mind, I'm focusing on the 256-bit case where we are executing 8 iterations of the innermost loop body at once. And the way we have to load data from memory is this, load data from the particle array into the YMM registers. YMM is just the name of the registers that we have for the 256-bit. So I've indicated here the X positions for 8 contiguous particles. So particles sub j dot position dot x, particles sub j plus 1 dot position dot x, and so on and so forth. And the idea is we got to get each of those, light blue boxes into each of the individual components of the YMM register. And the way we do that is with 9 instructions. 2 of these vmove ss, 6 vinsert ps, and 1 of these vinsert f128. It doesn't really matter what they do. The point is that there's 9 of them. And that's just for the X position. Then we have to move on to the Y position. And again, to get all the Y data, it's another 9 instructions that are dealing, basically loading memory and shuffling it around to be able to store it in a YMM register. And then again, the same thing for the X, or for the Z position. So the time being spent in the innermost loop is not just loading from memory, but also collecting all this data, organizing, shuffling, the shifts, XORs, vector shifts, vector XORs, that kind of stuff. So what can we do about it?
Pivot the memory base so you have all the X's together, all the Y's together.
Yes, so that's exactly right. If we were able to get all of the X components of the position in a contiguous chunk of memory, and all the Y components in a contiguous chunk of memory, and the same for the Z components, we should expect some kind of improvement. I looked at the source code for the N-body application, and it was interesting. I really wasn't able in a short amount of time to actually change the real data structures to do that. So instead, I did something stupid. I did something I think is pretty weird, and if you ever tried to check any of this code, you would never pass code review. Your boss would think you're crazy. But this is what I did. I went through the whole particle array, and I made new arrays. I made just a brand new array just to hold the contiguous X components, contiguous Y components, the contiguous Z components. And before each frame, before we started processing each frame, I just went through the particle array and just copied, all the X, Y, and Z components into their own contiguous arrays. That's what I then fed into a modified version of the vectorized loop body, which then wrote back into my contiguous arrays. And before my frame was done, I split my data, back doing shuffles and weird moves and stuff, back into the original particle array so that the DirectX code could still read the particle array as it did before. And this is what the code looks like. The only thing I really changed is those particular access things now. So instead of accessing particles sub j, particles sub y, I'm just accessing my new arrays x, y, and z. And in the context, I've had to add some new code. I am straight up doing memory copies or memory splits, basically, before and after. Anyone hazard a guess at how much faster that made the code? Or slower? It's not slower. Twice as fast. Doing something stupid. Doing something that was completely counterintuitive. Why would you ever want to use 30% more memory? That makes no sense. But, just focusing on memory, we're able to get a 2x speed up compared to the 256-bit case that we had with the code as is. And, there's 42 frames per second. That's huge. You might think this was run on that really expensive and powerful 40-core machine, something like that. This is single-core performance on my laptop that we can go from 8 frames per second in the scalar case, get a 6x performance boost, basically focusing on high-performance vector code, and we give you that with the compiler if you you throw the optimization switches. Plus focusing on memory. We get a huge, huge, huge speed up. So, something that's important, people are commonly saying processors are getting faster than memory is getting faster. And that's absolutely true. But I don't really like the word, increasing faster than. It implies that there's a future tense to this. We're already there, right? High performance code, vector code, memory just really, really, really matters. If you're looking at something that uses 128-bit data or 256-bit data, It's great that you can hit the 256 bits and you think you're running the pipeline at full capacity, but without looking at memory, you're screwed. So, the takeaway from this vector portion, is be mindful of your data structures. Of course, when if you're working on existing code, I don't want to say this because this is a really overall bad idea, right? Don't make extra copies of your data just to have contiguous pieces in memory. It's really not good advice. But at least it'll give you a sense of what's really capable, and how much, how your data is organized, how it accessed just really matters when it comes to performance. A question?
Real quick, your organization of memory, was that counted as part of the frame rate? So when you did it was also part of the time spent? I just want to be clear that your code to organize the memory was counted as part of the frame rate.
So the question is, my extra memory copies, do they count against the frame rate? Yes, they absolutely count against the frame rate. I literally changed that innermost nested for loop. This is well before the frame starts and well after the frame starts and well before the frame ends. Oh yeah. Oh, I'm not lying to you.
And why are they not?
Sorry, what was that?
Why are they not as slow as doing it inside the?
Sorry, one more time.
Why
Sorry,
are they
Simon.
so slow is what he's asking.
Why are they so slow?
Why are they not?
Why?
Why
You
are
do
they not
basically
slow?
the same thing, but it's a lot faster.
Yes, well, because it's not in an innermost loop. Let me go back to the code. We'll just take a look at it for a second. I mean, they are slow. If I organized my data properly in the first place, I'm sure the frame rate would be higher than 42 frames per second. That's absolutely, I strongly believe that to be the case. I was lazy. I didn't actually rewrite the whole program to do it. I just really wanted to get the point across that contiguous memory really matters. Exactly. So, right, it only happens once per frame. Well, technically twice per frame, right? One is to collect the data, and at the end you spit it back. But really, all of the time, or most of the time spent in processing a frame is actually spent in that innermost loop that you probably can't see. That's the for int j equals 0, j is less than num bodies. Exactly. Yeah, it's an n squared problem as opposed to just running my mem copy once per frame. All right, I want to spend a little bit of time talking about alignment, especially how that pertains to vector code, because this is extraordinarily important. So the way I like to think about alignment is in terms of cache lines. So here's not the prettiest of zoom-ins of the L1 cache. It doesn't actually look blue or anything like that. But the way the L1 cache is organized, and the same with the L2 cache, it's organized into 64-byte lines. So when you're operating, you load 4 bytes of data, say from the L2 cache. 64 bytes of data will come into the L1 cache. It's the neighboring bytes of that 4 bytes that you accessed. And when we talk about cache lines, for the most part, the unit of measurement of cache is really the cache line. So if I'm accessing 32 bytes of data, which is 256 bits of data, which is basically the AVX 256-bit stuff that we were doing with the physics simulation before. This would be an example of an aligned access. And if I access the next 32 bytes worth of data, that would also be an aligned access. And basically what alignment's going to give you is what I like to call good cache line density. I don't know if that's a real word or not, but I use it anyways. Cache line density, what I mean to say is you're accessing 2 elements of memory, 2 30-byte elements of memory, but you're only accessing 1 cache line. That has good cache density, and that's good for performance. If, on the other hand, you're accessing 32 bytes of data that span multiple cache lines, you're going to get a performance hit. So all I've done here is I've just shifted where the load actually starts, what particle I'm actually starting on in the physics simulation. This would be an example of an unaligned access. And then if we access the next 32-byte chunk, that's also going to be unaligned. Collectively, these 2 accesses are unaligned. And there's poor cache density here. 2 accesses, the same basic 2 accesses as before, but you're accessing 2 cache lines instead. And on the physics simulation, we actually get an 8% performance loss in frame rate. was kind of neat the way I did this. I was trying to take the particle array and shift it in memory to guarantee that the axes are going to be unaligned. That's not what I ended up doing. All I had to do was start that J loop, right? You know, for J equals 0, J is less than num bodies, J plus plus. I just started it at 1. Right? I said for J equals 1, J is less than num bodies, J plus plus. That's all I did, right? It's executing one iteration less than it was before. Remember the first question that I asked at the beginning of the presentation, is less instructions yield faster code? No, it actually hit an 8% performance loss because of the instructions that we were emitting were causing unaligned memory accesses, which I think is kind of neat. So you know, the same performance statement as before. Be mindful of your data structures. Always, you know, how your data accessed and how it's accessed and how it's laid out in memory really matters. But also its alignment with respect to the cache lines, right? And the counter that I would use for this is how many cache lines are being accessed either per iteration of your loop, or how many cache lines are being accessed as a whole for the whole loop body. And the way to, if you can reduce that, you are going to get a performance win, and that generally translates to data alignment mattering. Question?
So are there any tools that can help us tell us when we're unaligned or when we're not accessing the cache at the right density?
So the question is, are there any tools to help us with cache line and ways to measure cache line density? There are, and we'll get to them in a little bit. Oh, there's tools for most of this stuff. It's pretty interesting, especially with vector code. You know, more modern vector code, as more and more things are getting, automatic vectorization is mattering more and more. And with the newest range of processors really nailing 256-bit codegen, right, this memory stuff is just getting more and more important. And you know, the situation that we've got with tooling has gotten better. But it's still not, it's not as great as using the Windows Performance Analyzer to figure out exactly how many file handles are opened by this and this, and it gives you beautiful, beautiful statistics. There's still a lot of work involved. That's what I'm trying to say.
Like the memory you get from, like memory blocks you get from malloc are going to be aligned on those 64-byte boundaries?
So the question is the memory you get from malloc going to be aligned to 64-bit boundaries? No, and you can't count on that, unfortunately. So malloc, and I'm actually not sure what new. The situation with new. But as of right now, okay, I want to spend a minute talking about this because I think this is really interesting. Alignment matters. I hope that's come across. Malloc, according to the C standard, will return something that is 8-byte aligned. 8-byte, not 32-byte aligned, but 8-byte aligned. If you need better, you have to use aligned malloc, which is something that we have in the Microsoft CRT. I'm pretty sure all the other CRTs do support that. And there you can say, give me this chunk of memory and align it to 32 bytes. We are working in the compiler to do that for you. Yeah, I just wanted to spend a few minutes talking about this. Yeah, sorry, we'll get to the other stuff in a second. Wouldn't it be cool if you just wrote your code and you called malloc, or you called new, or you're using, let's fast forward to C++ a little bit, you're using a standard vector, and you're using the standard vector, the normal allocators that come with that, whether you're on the heap or whether you're on the stack. Wouldn't it be cool if your code was being used inside of a loop body and the compiler detected that and it went back and it changed your data structure for you to make sure that it was aligned properly? Wouldn't that be nice? You wouldn't have to change anything? Side effects is that your code's going to run faster. That's not true, right? I mean, it could increase fragmentation. It could increase your binary code size. There are issues. We still need to work through that stuff. And I spent, I think, around 2 months working on that exact problem, figuring out what data structures, what arrays, what pieces of memory are actually being used inside loops, especially those that are being used in vector loops, and do our best to align those. I spent 2 months on the problem. We got to a position in the compiler where we knew the exact alignment of every single local array, every single global array, everything that was on the heap. We knew what it was aligned to, and we knew how to change it. Now, I was there, but I couldn't check the code in. So let me ask you guys, why couldn't I check the code in? Hint, same answer to every question that I've been asking, memory. It turns out I was using too much memory to capture that data in the compiler. This is weird. I know. Give me a second here. You might have to think about this. When you talk about compiler stuff, it's always a little interesting because, right, the compiler compiles stuff. When you're talking about code in the compiler, not the code that the compiler compiles, things can get a little confusing. Yeah. So I had all this stuff. I had all of the alignment data captured globally for the entire program, but the compiler was consuming too much memory to actually keep all that data around. And what that translated to was a performance loss. By performance, in this case, I actually mean compiler throughput, how fast the compiler compiles. And there was like a 10% hit because I was using 150, 200 megabytes of data to capture all this alignment information. And I couldn't check it in. Yes, that's why you make it an optional flag. That's interesting. That does blow up our ability to test. It doubles our test matrix, and our test matrix is already pretty damn huge. But that's we started with a discussion about alignment. It's sort of gone downhill. Let's go uphill a little bit. So we know alignment's important. We're working on it. We're doing our best. I can't promise this, but I really, really want to get something in for Visual Studio Update 1 for 2013, and hopefully for the next CTP, where we're going to address a lot of these issues. And yeah, there won't be a 10% compiler throughput hit. That's not going to happen. Okay, let's go back to the normal talk. So, things that we've been talking about so far, focusing on working set's important. The amount of data that you use is really important, but it's not always easy, unfortunately. So I want to give two examples of where this is a little tricky sometimes. The first is with bit field operations. So I've got this struct on the left that's got 4 bool elements to it, A, B, C, D. And then I got a function that's called setC. So you pass in a bool value, and it just sets the third element of this struct to that particular value. And in memory, you got an object of type S. It takes 4 bytes of memory. The C standard, or the C++ standard, says that bools are 1 byte, which is interesting because that's 8 bits of data to tell you whether something's true or false. But that was done on purpose. Of course it was done on purpose. It's the C++ standard. So each element or each object of type S is going to be 4 bytes in memory. And then when you actually write to one of those elements, the code gen that we emit for the setC function is 3 bytes long. It's just a move. Sorry, when I mean 3 bytes long, I mean the actual encoding of that instruction in memory is 3 bytes. And it's just a move instruction. We take what's in the DL register, which is the Boolean value V, 8 bytes or 8 bits of the Boolean value V, and we just do a byte store into memory into RCX, which is the pointer corresponding to S plus 2, so it's the third element down. And let's say I've got a lot of objects of type S in memory, right? And you might think, let's save some space. Instead of S being 4 bytes, if we switch it and use the old school C syntax with the :1 or colon a number, that's the bit size number. So what we've got here is a new version of S where each object of type S is only 4 bits. It's only half a byte. And that looks like a memory win. And in some sense, it is. Until you look at the size of the function body for setC, there are no bit storing operations that work for memory. There just aren't any. You can only load bytes, or 2 bytes at a time, 4 bytes at a time, or 8 bytes, or 16 bytes at a time, or 32 now. You can't do bit manipulation. So in this case, we have to mask off this C element of the S, which is stored in RCX, and then we shift what comes in the D register in EDX, and then we store that into memory, and it's 11 bytes. The code size is 11 bytes. So you got to ask yourself, how much are you really saving by changing your data type here, especially going to bit field specifically? And you might back. You might say to yourself, hey, I've got this setC function. It's only being written once. I'm only paying a penalty going from a 3-byte code size to an 11-byte code size. I'm only paying that penalty once, and I'm saving all of this extra memory because there's a lot of objects of type S but you also have to take into account the effects of inlining. If you have that setC function and it's being called in 100 places that are all really hot, chances are we're going to be inlining that setC function for you, and your code size will be bloated. So it's not always straightforward to just say, hey, I only wrote this code once, but you've got a set A function, a set B, a set C, a set D function. You've probably got a clear A, clear B, clear C, clear D, and maybe a set A, B, C, and D as well. So you're probably looking at 12 functions that are going to be modifying this. And for the most part, you really do want those functions to get inline for performance. And there will be a code size bloat for it. So it's not always easy to just purely focus on working set when you're talking about bit fields. And I guess the tool that can help with this is you can look at the output of the compiler, the actual assembly file, assembly listing, along with the byte encodings for each instruction. So it's the slash, capital A, capital F, capital A, lowercase s, lowercase c. The C is what's interesting, is what's going to tell you the code bytes for each function. And you can look at the code size from there. And that's going to tell you the code size and all that kind of stuff after inlining. The second example I want to do is array of structs. So let's say I've got this struct called myDataType. It's got 8 elements in it, floats, A, B, C, D, W, X, Y, and Z. And I've got this big array of these myDataType things. It's a bug. Let's just say I happen to know that my A, B, C, and D fields are really hot. They really matter for computations, and my W, X, Y, and Z are really cold. So maybe these are the final results of some complex computation, or whatever. You can, I'm sure, think of examples for that. The way my data array is going to be stored in memory in terms of 4 elements of hot stuff, 4 elements of cold stuff, 4 elements of hot stuff, 4 elements of cold stuff. And what it really matters is if you look at this diagram, another beautiful cache layout diagram that's just nice and blue. Right, I've got the execution pipelines on the left. Those are my 6 instructions per cycle pipelines. Pretty expensive core. And if I access 4 bytes from my data and say the data is in the L2 cache, we're going to bring that data into the L1 cache and all the data that's around it, right, 64 bytes at a time. And then we say we access the 4 bytes of the next element, and we again bring that data into the L1 cache. The deal is we're wasting room in the L1 cache with cold data. There is no point in doing that. Why? In this particular case, why are we wasting half of the L1 cache, right? You could just take a computer and run it with less, just turn off half the cache and you're going to get the same performance. It's just a huge waste. So the way to get around that is, step 1 would be split your data type up into hot data and cold data. That's what I've done here. I've just given it a really bad name called my hot data type and my cold data type. But you could think of making a subclass with your computed data and a subclass with the final data, something like that. And just we now have 2 arrays instead of 1 array, but all the hot data is contiguous in memory, and then all the cold data is contiguous in memory. And that stuff can stay in main memory. It doesn't have to pollute the caches at all for us. And I just wrote a really small micro benchmark for this that just modifies some of this stuff in here, and I got an 8% speed up just from separating the data types. Right? So I haven't changed any of the loop bodies, none of that. All I've done is changed how the data is laid out. To make sure that the hot stuff is together and the cold stuff is together. The second thing you could do, right, in an ideal world, you should, if your hot data type stuff is being used inside a loop, you really should consider making A an array, B an array, C an array, and D an array, like we did with the n-body example, but hopefully without any extra mem copies. But sometimes that's not always feasible. Sometimes you can't just change the core data structures of what you're working on. Right, a lot of us are probably working on older code. But maybe something like this, where you break a structure into multiple structures, is a lot more feasible, and you're definitely going to get a win from that. So, just to recap stuff that we've talked about, watch your access patterns, right? That matrix multiply example, right? We didn't change the innermost loop. We didn't change the data types. We didn't change anything about the arrays. All we changed is how memory is being accessed, the order in which the memory accesses show up on the wire, and we can get a huge, huge performance from that. You want to keep your data as close to the execution units as possible, especially when you're doing multi-threading. Multi-threading of I/O-bound code. And if you're looking at vector code, there's a very, very good chance that it is I/O-bound. So keep an eye for that. Alignment matters, right? Especially for vector code, you want to be looking at cache line density. Get your cold data out of the way, I think is a nice way of saying, instead of keeping your hot data together, just get the cold data out of the way. It's probably good, good advice to code by. But be careful. It's not always straightforward. Like that Bitfield example where you think you're doing the right thing, but maybe it's not working as well as you think it would. So in terms of resources, things that you can do, programs that you can use to help, I like using the Visual Studio Performance Analysis stuff. That's going to tell you what code in your program is hot or what code in your scenario is hot. If you need information specific to caches, how many L1 cache misses, how many L2 cache misses, how many L3 cache misses, how many of those cache misses are due to alignment restrictions, or how many of those cache misses are due to the memory bus is currently in use because another processor is using it, stuff like that. You're going to have to go to the hardware vendor performance analyzers. So Intel provides the VTune program, which is great, and AMD provides CodeXL, which gives similar information. You can really dive deep into process counters, or processor counters, CPU counters, and that's what those are really going to give you. So this is sort of you want to do a mix of these things. Sometimes the Visual Studio Performance Analyzer is good enough. Sometimes you got to go really, really deep into VTune or very, very deep into CodeXL. Some other tools, so things that are baked into the compiler, the FASC switch is going to give you the assembly output, including the actual bytes that represent the instructions. That's going to give you information about code size. You can also look at the assembly of your hot loops and just take a look. I don't know how many people actually read assembly code anymore other than me, but it's, it's really useful. It's also really cool. I like looking at assembly code. There's a linker switch /map, which is going to produce a map file. That's going to give you info about any global data, including its address. So that'll tell you if any of your global data is unaligned, which is extraordinarily useful. There's an undocumented switch. This one's a doozy. /lowercase d1 report single, capital S, class, capital C, layout, capital L, and then you give it the name of the structure that you want to see the class layout or structure layout. That's going to give you how the compiler is going to lay out your class, or how it's going to lay out your structure. So if you got a struct that's got an integer followed by a bool, followed by an array, followed by a pointer, and the struct is called blah, you can do CL D1 single report single class layout blah, and you're going to get a visual aid as to how the compiler is actually read, how it's laying your data out. This can be really useful, especially for sometimes you just look at the code and you don't have all the data types accessible to you. This is going to give you right from the compiler how your data is going to be laid out for that structure. I think that one's a really useful switch. You can search for it on the internet. You'll see some blog posts where we reference that. And the last thing is a program that you guys might not know about. It's pretty new. I think it came out in 2012. It's called VMMap. VMMap is a sysinternals tool from Mark Russinovich, and it tells you basically all of the memory information from the operating system's point of view for your program. It's going to give you all the info about the working set, the private data, all that kind of stuff. It's going to tell you what of your data is on the heap, what of it's on the stack, how much stack space is left. It also updates in real time. This can give you some really interesting information of sort of where to start looking in your program for memory issues. I really like using VMMap. Take a look at the compiler switches. Oh, sorry, I'm switching topics here. So in terms of overall performance, so not just memory anymore. I'm taking the memory hat off. I've had it on for an hour now. But now we're just talking overall performance. Take a look at what's going on in the compiler switches. There's stuff in there that we add new switches all the time. Take a look at the floating point switches, FP-FAS in particular. There's frame pointer omission on x86 code. There's sort of a lot of extra stuff in there that might be interesting if you haven't seen it in a little while. We also have the automatic vectorization blog and the vectorization cookbook. That's on the native concurrency blogs. That was done by Jim Hogg, the program manager on the compiler optimizer team. And it's sort of guidelines, general guidelines of how to get the best performance out of automatic vectorization. We also have the Visual C++ blog, and Jim Hogg, writing on the Visual C++ blog, is giving a blog series about compiler optimizations. Check that out. It's really cool. I work on that team, so I think it's really cool. And then there's also the Channel 9 Going Native stuff where there's interviews. A lot of it's dealing with performance of native code, the standard template library, stuff like that. Before we finish up, I got to give a shout out to the user experience guys in room 254. All day today, they're doing a user feedback study for the next series of versions of Visual Studio. So if you wanted to, take give some feedback on the user experience, please go check that out. It's room 254, and they're there all day. Just go and stop by. And that's about it. That's everything I've got with memory. If you guys want to know more, please put that in the feedback that you guys give. If you're interested in compiler optimizations, if you're interested in other aspects of native code performance, please let us know. We'll work something out. I love talking about this kind of stuff. So yeah, there we go. Thank you.